Hello students, in this video we'll find a formula for the Christoffel symbols in terms of the metric tensor. Given a covariance basis, E1 through En, just call them EI, depending on coordinates UI upper in the natural way. What does that mean? That means that these EIs arise from the partial derivative of the vector field position with respect to these components UI, okay? So that's how these covariant vectors are formed, right? And of course, these covariant vectors transform in a particular way, which we know well. Now, we also know that if I differentiate these covariant vectors with respect to the coordinate frame, then I get these Christoffel symbols. And this implies that if I do partial EI with respect to a vector uj, I get these Christoffel symbols, gamma ij k, with respect to the covariant basis ek, okay? And so what I'm going to do is I'm going to try to find a formula for these Christoffel symbols by differentiating the metric tensor relationship, right? And so now recall that Gij is EI dot EJ is the metric tensor. The Riemannian metric tensor, okay? It's a two covariant tensor. And so now I'm going to differentiate this relationship with respect to UK, okay? So this implies that partial Gij with respect to UK is going to be what? If I differentiate with respect to the coordinate UK, I'm going to get partial with respect to UK of EI dot EJ. And so this is going to be EI dot what? Dot partial EJ partial UK plus partial EI over partial UK dot EJ, okay? Just by the product rule. And now we can use the definition of the Christoffel symbol. I'm going to need some dummy indices, okay? So this becomes what? This is going to become EI over there dot what? I'm going to have EI dot, I'm going to have a gamma JK, I'm going to put an L up top over here, and then EL, like so, plus EJ, I'm going to switch the order because it's commutative. Then I'm going to have a dot what? Dot gamma IK, L, and then EL, like that, okay? So this is going to simplify to what? This is going to simplify to a gamma of JKL, and then a GIL, like that, okay? And this thing over here is going to be a what? And the order doesn't matter, right? So I'm going to put this as a GJL, and then a gamma IKL, all right? And these expressions are important. Actually, what these things are called is these expressions are actually called Christoffel symbols of the first kind, right? Typically, it's better to start with the second kind Christoffel symbols, but what these things are written as, and just going to make a note of this because you might see this in some textbooks, is that you're going to see that if I look at something like, if I look at G of AB, and I look at gamma of CD, and I put a B up here, what this becomes over here is this becomes gamma. I'm going to contract on this and bring the A downstairs and so write gamma of A, CD like that. And this is called the Christoffel of first kind, Christoffel first kind. And then these things over here are actually called Christoffel second kind. These are Christoffel second kind. The terminology is sort of irrelevant. Okay, excellent. All right. Now, I'm going to cyclically permute this relationship. So let's cyclically permute this, and what do we get when we do that? So then, I'm going to look at, by the same sort of principle over here, I'm going to look at, so we're going to cyclically permute. We'll yield. I'm going to look at partial, and I'm going to look at a GJK partial UI. Like that. And so what's that going to give me over there? So I'm going to replace, so everywhere I see the I and J's get replaced with K and J, right? So this is going to give me what? a gamma, the L stays the same, right? And then playing the role of J and K are going to be K and I. So I'm going to have a K and I over here. So a K and I. Remember, these things are commutative, so it doesn't matter. Then we have a G what? Then we're going to have a, now the I is replaced with a what? The I is replaced with a J, right? So I'm going to have a G, J, and then a what? And then L over here, plus what? And then over here, so the J was what? The J gets replaced with K, so that's going to be a G. So J gets replaced with K. And then what's going to be replaced with, so then I have an L, and then I have a gamma L, and then an I, which gets replaced with a J over here. And then I have a K, which gets replaced with an I, so gamma I, Ji. And what? And I'm going to cyclically permute one more time. G what? G Ki partial Uj is going to be what? Now my I is equal to K, so this is going to be what? This is going to be a Gi, but my I is now K, Gk, and then an L, then a gamma L, and then a J was really what? J is really an I, and then K is really a J in this case, plus what? Plus G, what was my J here? My J is really my I in this new case, I, and then my what? Then my L is still my L, gamma L, and then my I is really my K, so I is really K in this formula, and K is really a J, like that, okay? So I have these three different relationships over here, and what I really want a formula for is I want a formula for gamma of IL, right? So I'm after this quantity over here, and I'm after what quantity? I want the gamma of ILJ, right? So then I'm after this quantity over here, right? Because what I'm going to do is I'm going to say that this quantity over here is exactly the same thing as I can replace this. Note that this other thing over here is really nothing more than just GKL gamma IJL, okay? So what I'm going to do is I'm going to look at, now consider, here's the key part of this. So let's look at 1/2 partial G IK partial UJ plus partial G JK partial UI, and then plus, I'm going to do a minus actually to make sure I get the symmetry right, minus partial GIJ partial UK, right? So let's see what these things are going to give us. Now, of course, there's going to be 2 of every term over here, so it's going to be a 1/2 of what? So GIK is going to be this thing over here. It's going to be GKL gamma IJL plus GIL gamma LKJ. And I'm going to add to that this expression over here, the KJ term over here. So that's going to be added to a GJL, JL, and then gamma IKL by symmetry, and then plus a GKL, and then a gamma IJL, and then finally minus these terms up here that we started with, right? So minus GIL gamma JKL, and then minus GJL, and then gamma of IKL like that, okay? So let's see what's going to happen over here. It looks like it's a huge mess, but notice, of course, what's going to happen. I have a GIL JK, so this term over here, let's look at this term over here, and this term over here. Well, it's going to be a GIL, a gamma KJ, or gamma KJ, or gamma JK. Those things are the same by commutativity of the Christoffel symbols. So this term over here and this term over here cancel out. Now let's look at these next terms over here. If I look at this term over here, let's look at this term over here, and this term over here. Well, those are GJL, GJL, and then gamma IKL. So those terms are equal and opposite, so those terms cancel out. I'm left with a GKL, gamma IJL, with 2 of them, right? So this whole thing simplifies to what? This whole thing is going to simplify just to a what? Just to a GKL, and then a gamma IJL. So now I can hit this with the inverse and get my conclusion, right? So if I hit this with the inverse, because the inverse of GKL lower is GKL upper, right? So this is telling me that gamma IJL, the Christoffel symbol of the second kind, is 1/2 G upper KL, and then what? And then partial G metric tensor IK over partial UJ plus partial g jk partial ui minus partial gij partial uk. And this gives me a representation formula for these Christoffel symbols. This is actually called the intrinsic representation of the Christoffel symbol. So I'm able to write in terms of the metric tensor and the inverse of the metric tensor. So what we have over here is we have this formula which allows me to sort of get all sorts of really beautiful properties of these Christoffel symbols. This formula may look more complicated than the dot product of the derivative of these basis vectors with respect to the other, but these metric tensors in particular in sort of these orthogonal curvilinear coordinates, these expressions are all, this metric tensor is diagonal, so these expressions collapse a lot when you look at very special coordinate systems. So this representation of the Christoffel symbols is very useful in finding particular instances of these of Christoffel symbols in terms of very special coordinate systems like spherical coordinates, parabolic coordinates, oblate coordinates, all sorts of different coordinate systems. It's very easy to compute Christoffel symbols using this representation in terms of the derivatives of the metric tensor with respect to the coefficients hit with the inverse metric tensor symmetrized. Thank you very much.